Good afternoon, ladies and gentlemen. I'm really excited to see you here today. I'm Mike Aizatskyi. I'm from App Engine engineering team. And today I would like to talk to you about App Engine and MapReduce. So the agenda of today's talk is to go briefly through MapReduce computational model, because I assume some of you would like another reminder of what it is. Then we'll remember the map library, which we now released like a year ago at previous Google I/O. Then I'll make a couple announcements. And I'm going to talk about some technical stuff to get you interested in how we did some things in App Engine team. And throughout the whole presentation, I'm going to show you several examples and demos just to keep you entertaining. So let's start with MapReduce computational model. You might know that MapReduce was created at Google many years ago to solve problems of efficient distributed computing. And really, absolutely every team uses MapReduce for something. I'm absolutely sure that even Android team uses MapReduce for doing some stuff, for doing some calculations, statistics, whatever. And it's been a real success at Google, and we use it for everything. And this is the diagram of how it looks like. It might be a little bit confusing, so we'll go through it step by step, but it basically has three major steps, and those are called map, shuffle, and reduce. So the map shuffle is some kind of user code which runs over input data. That input data might be database, some files, whatever. And the goal of the code is to output key and value pairs. And the MapReduce framework should take those key value pairs and should store them somewhere for other steps to consume. And as you see, the input is usually sharded, like split in parts, so that all of them can be processed in parallel really, really fast. And as I said, this is user code. The second step of MapReduce is a shuffle step. And the shuffle phase has to collate values with the same key together. It has to go through all the values which are generated by map phase. It should find same keys. It should bundle those values together. And it should output key and list of value pairs. And this step has no user code whatsoever. This is a generic step of MapReduce framework provided usually just as some kind of service, as some kind of magic black box which does shuffle. And the third part is reduce. And the reduce function will actually take the shuffle output, which is a key and list of value pairs, and it does something with that. It might compute something more interesting from that data. It might save it to database. It might do something. And this is, again, the user code. And again, its goal is to process the shuffle output as fast as possible, and it's good if it's parallel. So once again, this is the diagram of MapReduce computational model, not the implementation, but just the model. So we have map step, key values, shuffle, bundles, same keys together, and reduce processes the shuffle output. So the way we work at App Engine, we usually take something which we already have at Google, and which works for Google, which works for us, and we give it to you. We give it to our developers. We bundle it somehow, and we give you access to that same set of technologies. And this is exactly what we wanted to do with MapReduce. But when we started working on that, we realized that there are lots of problems with this approach unique to the App Engine. First of all, App Engine has scaling dimensions which we usually don't have at Google. App Engine has lots and lots of applications, much more than Google applications. And we expect many of them that will run MapReduce at the same time, and that might cause additional scalability problem. The other problem is isolation. We do not want anyone running something to, to kill a royal wedding website. If you run MapReduce, we want royal wedding to be up, so we want to completely isolate all applications from each other, but still we want them to have good performance. It might be surprising, but we also want to rate limit. Originally, MapReduce at Google was designed to go as fast as possible. It wants to process all the data in shortest amount of time possible. And that means that we can consume thousands of dollars resources per minute. And not everyone is happy about that, because you might run MapReduce and it will consume all your daily resources in 15 minutes, and it will kill your online traffic. So you might want to rate limit it and say, okay, don't run in 5 minutes, please run over 2 hours, because I have short-term quotas, which I don't want to consume. And taken to the extreme, there are even free apps which have a very, very limited amount of quotas, and they still want to run MapReduces. And they might say, OK, run this for the whole week, but just get it done. But please, please, please do not kill my application, which is not a goal for MapReduce, Google's MapReduce, to run as slow as possible. And they also have a protection issue, too, because there are lots of users out there. Some of them are malicious. Some of them are just not doing the right thing. And we want everyone to protect from each other. We want to protect Google from you. We want to protect you from each other so that nobody steals all the data. So when we analyzed all this, we realized that it's not a really good idea to take the Google's MapReduce and give it to you as is. That we realized that we need to do lots and lots of additional work. And that's why a year ago, we released the MapReduce Library, which implemented the first step of MapReduce, which is map phase. We released it at Google I/O 2010 in this building. Since then, it's been heavily used by developers everywhere, outside, inside Google. We even use it in App Engine team. We use it in admin console. We generate reports with that. We have new indexer pipeline, which is in the works, which uses MapReduce Library. And lots of people, like there was recently a blog post about guys using this MapReduce Library, which is already useful. And during the whole year, we've been working on improving that. And we had quite a large set of improvements to the library. First of all, let me go through some of them. We have control API, so that you can programmatically control your jobs. So that you can, for example, create a cron job, which will run every day and start Mapper. We have custom mutation pools, which is a way to batch some work between map function calls and process it more efficiently. We have namespaces support, so that not only you can run your mapper over some fixed namespace if you use namespace or several namespaces. You can even run mappers over namespaces, not the data inside namespaces, but just over namespaces so that you can analyze your namespaces. You can do some kind of migration, statistics, whatever. We have implemented better sharding with scatter indices. So we think sharding is now pretty good. And there are many more small improvements to the library. So if we take a look at this and we ask a question, what should we do to take MapReduce Library to MapReduce Library? And the first thing is we need some kind of storage for intermediate data, because map jobs, they tend to output lots and lots of data in MapReduces. And for that one, we designed the Files API, which we'll go through in more detail later, and released it in March 2011, just 2 months ago. We also have to implement the Shuffler service. And Reducer is not a problem, because Reducer is actually the mapper. It just goes over shuffle output. And of course, we have to write lots and lots of glue code. So today, I'm happy to say that we're launching the Shuffler functionality. And this actually has like 2 different functionalities. First of all, we have a full in-memory user space, task-driven, open-source shuffler for kind of small data sets. And small, I mean like hundreds megabytes, maybe gigabytes, maybe even more, who knows. This is completely open source for Python. Java comes soon. It will be open source too. We also announced that we want to start trusted testers access to Big Shuffler. So if you have some kind of data sets which you need to run MapReduces on, if you have hundreds of gigabytes of data and you want to run MapReduces, just get in touch with us and we will see how it works for you. And we also, of course, releasing all the integration pieces which are needed to run your MapReduce jobs. And they are part of MapReduce Library, which we're now starting to call MapReduce Library. It's not a map library anymore. So without going, we'll go to the technical details later, but first let's go through some simple examples of how MapReduces look like. And the first really simple example, which is the hello world of MapReduce, is a word count MapReduce. And this is the goal of MapReduce is to take some set of text, and calculate how many times a single word appears in the text, like basically statistics of distributions. And map function is really simple. It's almost like 2 lines, even if you throw in some additional declarations. Basically, you split the text in words, and you yield word as a key, and empty string is a value. We're not using values here per se. We're just going to need them to count those. So if you take the famous quote from the Pulp Fiction, then for 5 words, we can output 5 key value pairs. Then the shuffler will take this data, will process it, and then we'll bundle all values for the same keys together. So we'll have 3 pairs. That's that baby, and that's going to have all 2 values from the input, which are empty strings. That's also 2, and baby is going to have only 1. And reduce phase just ignores values. It just counts how many of those there are. So it's going to output that that's 2 times, that is 2 times, and baby is 1 time. So let's see how this works. Is it large enough? Okay. So unfortunately, this stuff runs for several minutes on the data set that I chose, so I decided not to run it like directly. And I took 90-something books from Gutenberg project, which amounts to tens of megabytes of text. And I ran this MapReduce. It took 6 minutes. And you can see that this is our new UI for like multi-stage processes. We're going to talk a bit about this a little bit later. But we can see that the whole MapReduce talk took like 6 minutes, 40 seconds. Map phase took 1 minute, 40 seconds. Shuffle took 3 minutes, and reduce took 1 minute, 50 seconds. And there are some additional steps like cleanup and some system steps. And if we take a reduced job, which has finished in a minute, like here it is, 1 minute, 48 seconds, we can see that it read 78 gigabytes of intermediate data, which is quite good. I told that Shuffler is supposed to process hundreds of megabytes, but we're actually being able to run it like over 78 gigabytes without big problems. And it output like how much? 1 gigabyte of data. And the total input size was just total input size. We have like 50 megabytes of text of books. This is how it outputs looks like. So we have all the words, which are in some order. They're kind of sorted, but we'll talk about this later. But we can see that captivity or like I don't know what it is, but it's actually present only once. So if we use some kind of grep, on this word, we can see that it actually happens only once in this only book, and yeah, it works. So this is the word count MapReduce. And now let's improve our word count MapReduce to build the simplest possible, really useful MapReduce, which is a building block for even for Google.com. And this MapReduce is called built-in inverse index, which means that we want to build a huge map which allows you to look up which documents have the given word. And this is, you can actually say that this is how Google.com works. So if you have internet on your CD-ROM and you upload it to App Engine, then you can build a Google.com search index. So we do the same stuff, but instead of ignoring file name, instead of outputting empty strings, we output the file name or document name or something which identifies where this word comes from. And the only thing we do in reduce, we just remove duplicate values. We just build the list that this word is going to occurs in this document, and this document. Of course, instead of just deduplicating documents, you can calculate how many times it occurs in documents. So later you can compute some kind of ranking, whatever. But this is like the simplest one. And again, I'm going to show you that it's actually ran a little bit slower for some reason. It's like non-deterministic time. But yeah, it took 6 minutes, 50 seconds. And if you take a look at the size of intermediate data, here it is. We can see that we actually processed 170 gigabytes of intermediate data, and the whole MapReduce took 6 minutes, which we think is actually quite good. So, and here is how the output looks like for the whole 60 megabytes of books from Gutenberg project. So you can pick, now you can get this document, and you can actually build a web service which does some kind of search here. So if let's verify that it works. Let's take a look at aviators. here it is, grep -e aviators for everything. And we can actually see that there are only 2 documents which have these words, 1059 and 3601, which is true. So I'm quite confident that it works. So these were 2 most common and the simplest MapReduces you could write. And later in this talk, I'll show you a little bit more complicated and interesting MapReduce. But now I would like to dive into technical bits of our solutions. I'd like to talk about how we did what we did. And actually, I would like to show you that you could build something, or you can build something similar or modify it to your needs now that you know how it works. And I'm going to talk about 2 things. I'm going to talk about Files API. This was our solution to MapReduce storage problem. And I'm going to talk about user space shuffler, about how we build it, which algorithm do we use, and so on and so forth. So Files API, as I told you, and as you have seen, MapReduce jobs generate lots of intermediate data. This was a tiny, simple MapReduce, which is just an example and processes just 60 megabytes of input data, and it generated 170 gigabytes of intermediate data. And of course, you have to store it somewhere. So before Files API, we had 3 storage systems. We had data store, which is kind of expensive because it's replicated over the multiple data centers, lots of copies. And it also has 1 megabyte entity limit, which makes storing 170 gigabytes of data kind of hard. You have to split it. You have to remember where you put each chunk. You have to read it in order. It's not a pleasant task. We also had a Blobstore, which is really good, but it's read-only. The only way you could get data in, you could upload files through HTTP form, which does not work for MapReduce. And you had memcache. Memcache is kind of good. It's really fast, but it's small, and it's not reliable. You can never be sure that the data you put in is still there, because there might be memory pressure or something else. So that's why we designed the Files API. We wanted to give you a familiar files-like interface to some kind of virtual file systems. These are not local files. These are virtual file systems. They look alike local files. If you have ever accessed local files, you will find it familiar to you. And we released it at 1.4.3. We integrated with MapReduce Library the way I'm going to show you. And we kind of consider it to be a low-level API. It's not something that every user we think is going to need. Most users will probably just use MapReduce Library. But you might find some interesting needs for this one, too. And it's also still experimental library, experimental API. We're still looking at how it works. We're still trying to understand what you need, what we need. And this file, I said that the API is really familiar to local file system, but it has some huge differences. And basically, the biggest difference here is that files have 2 states, writable and readable. In writable state, you can write the file, but you cannot read it. In readable state, you can read it, but you cannot write to it. And all files start in writable. Later, when you're done writing, you can finalize the file, and you can transfer it to readable state. There is no way out of readable state. Once it's finalized, it's forever. All writes are append only, so there is no like random access. All writes are atomic, meaning that if you output 100 bytes, then nothing is going to get in between of those. And they're all fully serializable between concurrent clients, meaning that you might have lots of background tasks, lots of task queue tasks right into the same file at the same time, and we're going to make sure that all the data does not interleave between them. And we also say that some concrete file systems, they might have some additional APIs for dealing with their own properties, and every file system is going to have their own like reliability or like availability constraints or guarantees. Files API does not know about that. And in March, we released the first file system. This is a Blobstore file system. So we actually took the read-only Blobstore facility and we made it writable. So you can now write directly to Blobstore. You can create really huge files. There is no like limitation aside 64-bit length, which I think is going to be enough for next 1,000 years. And once you finalize the file, those files are fully durable. They're going to be replicated across multiple data centers, and they're going to have same reliability guarantees as high replication data store. But important point here is that writable files are not durable, meaning that if something bad happens, for example, we have data store failure, or we might have a maintenance period, so you might lose your files while they're in writable state. We did it especially so that while you write, we don't replicate it, so that latency is good. And because we think that MapReduce is going to be the primary consumer of this API, okay, if something bad has happened, we're going to restart MapReduce job. And since this is a Blobstore, you can fetch a blob key for finalized file and use the familiar Blobstore API. So if you want to download that file or serve it to the user, you could get the blob key and serve it directly to the user without writing too many code. This way you can create you can write a code which generates some kind of movie. You just write the Blobstore frame by frame, then you finalize it, and you can serve it. This is a simple Python example of how you could access it. Java has its own API, and yeah, we don't have much time to go through all of those, but basically it looks familiar to the language. It's mostly like the files you have in Python. So first of all, you create the files in Blobstore, and you specifically say, okay, I want a file from Blobstore. Then you open it for write, you write data, and once you're done, you say, okay, finalize the file. To read it, it's the same stuff. You can open file, you can read from it, you can seek in the file. Write is append only, and read can have random access, so you can do lots of crazy, interesting things. And if you want to get blob key, just call get blob key function, and you're going to get a blob key from file name. And as I said, we integrated it with MapReduce Library. We added some kind of output writer support. So with one line in MapReduce.yaml, you could just specify, okay, I want the output of this mapper function to go directly to Blobstore. This way, by having single line map function, which just transforms entity to CSV line or like XML, whatever, you can easily write a mapper which will export your data into Blobstore. And since we have control API, you can actually create a cron job and do a copy of your data every day or every week or run it whenever you need. We also plan to migrate bulk downloader and uploader to this functionality. We're not there yet, but it will eventually come. But meanwhile, it's now easy to get the data in some sort of downloadable format. And we also have some low-level features, which I'm not going to spend lots of time, but basically we have exclusive locks. You can lock files. You can make sure that no one else access it. And we have sequence keys so that if you need some kind of guarantee that you haven't written the data you're already writing, because request might be retried, task might be rerun, or request might come the second time from the user, there is some notion of sequence key, and the API will take care of you. Just if you need this, read the API documentation in source code. And in the future, we're going to introduce more file systems. The first one, which we really, really want to get out, we call it temp file system. This is going to be much faster, much cheaper, because it's not going to be replicated anywhere, but it's not going to be durable at all, even finalized files. You might lose those if something bad happens, and you're going to have each file be stored only for several days, because we want this to be a MapReduce baked-in file system. We want it to be really fast. We want you to be able to store terabytes there without selling your house. And another thing is that we want to integrate with other storage technologies which we got at Google. Yeah, just keep looking at what we're doing, and we're going to have lots of exciting file systems coming. So this was Files API. And now let's talk about the bread and butter of our MapReduce implementation, which is user space shuffler. So as I told you, we're going to have two shufflers. The user space, which is kind of simple, open source, and it has its limits on the data it can process. And we're going to have a huge shuffler service, which is hidden, which is just an API call, which says, OK, shuffle this for me, and it's going to process lots and lots of data really, really quickly. But we wanted to have user space shuffler for small and medium jobs. And as you remember, the job of the shuffler is to consolidate values with the same key together. So look around the data, find those same keys, values together. And even that we want to have this user space shuffler, meaning that it's in full source code, it has no new app engine components, anyone could have built something like that. We still want it to be reasonably fast, reasonably scalable, and reasonably efficient. Because you saw that, yeah, 170 gigabyte is not a big deal. It's just a couple minutes, which is good. So the way we're going to arrive at shuffler implementation is we're going to start with really, really stupid shuffler, and we're going to improve it step by step until we get to the final algorithm. And the first and obvious shuffler is just load everything into memory, sort it, and read that sorted array. This is going to look like this. Once you have your values sorted by key, you can just read and see, OK, this is the same key, grab this value, same key, grab this value. OK, this is another key. Here are your values. And it's really easy. It's just a couple lines of code. But unfortunately, it has lots of problems. First of all, it's memory-bound algorithm. Like how much data you can fit in memory. Like if you're having a separate workstation, like server computer, you might be lucky to have, I don't know, like 64 gigabytes. So it's actually memory-bound, and there is no way to increase performance by throwing more resources at it. Because it's single thread, you just sort it, no way out of it. So we're going to improve this one by chunking our input data into chunks and store that data into files API. And then each chunk will be sorted by its own. So those chunks should be like of some size. Because we're running an app engine, it's not, and in Python, it's not really memory efficient. Our chunk size is like 5 megs. So we're going to sort each one of those, store it, and then we're going to merge sort all chunks together using external merge. Or even as MapReduce Library does, we're just going to merge read without sorting. Just merge read from all of those. This is really simple. You upper two blocks go to the first chunk, lower 3 to the second chunk. And then you're going to merge read by maintaining pointers into each one of those. You read from all of them. You see, OK, blue, 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 blue. Then you move each one of them. And yeah, it's going to work. And the properties of this approach is that, first of all, this is no longer memory bound. You can sort as many chunks as you want, as soon as each one of those fit in memory. Another good thing that this sorting is parallel. You can throw in 1,000 computers, give each one a chunk, and they're going to finish in parallel. But unfortunately, the merge phase here is not parallel. It's just one phase on single computer, which has to merge read all of them. And it is kind of difficult and slow to merge read from too many files. Like if you have 10,000 of files, you should have some kind of heap structure to maintain pointers into 10,000 of files. Yeah, it's getting really, really slow once you crank up number of files. So we're going to improve this too. And the way we're going to improve it is we're going to use the hash code of the key. So it's trivial, like if hash codes of the key is divisible by 2 and not divisible by 2, then we can process all those keys, 2 keys separately. Like all even keys go to one chunk, all odd keys go to another chunk. And we can run the same algorithm from the previous step on all those chunks together. And we don't have to worry about merge reading all of them because each one of them has different hash keys. This is how it's going to look. It looks quite messy now, and I needed the forced color. But basically, once again, we take a look at each block output from Mapper. We separate it into chunks by hash code. Like blue and red goes to the top. Green and yellow goes to the bottom. Then we sort data from each hash chunk. So we sort some greens and yellows, we sort some blues and greens, and then we're going to do merge read from only those chunks. And this approach is actually quite good, because by having hash code, you can split your output data into as many hash code-based chunks as you want. You want thousands? You got it. You want 10,000? So you can have merge as parallel as possible. You can run thousands of merge reads in parallel. All sorting is in parallel. There is no memory-bound thing here. If you have to read too many data, just increase number of hash chunks and process them separately. And this is actually the shuffler which we released today for Python. And the Java version is going to come really, really soon. As far as I know, even someone is already working on that. And yeah, this was the shuffler. This is the way it works. Of course, the code is more complicated than that because you have to deal with lots of tiny details, but this is the idea. And we soon realized that our MapReduce, it consisted of several offline processes like map. You have to finish map before you start shuffle. Shuffle, you have to finish shuffle before you start reduce. So we designed it in UAPI to chain complex works together, and we called it the pipeline API. And this is actually the glue which holds the mapper, shuffle, and reducer, and which makes it the single MapReduce job. And our MapReduce library is now fully integrated with pipeline. And that UI which you saw with multiple stages, that actually comes from pipeline API. It's the API which takes care of all that detail that, okay, after you're done reducer, you have to run cleanup jobs to clean up all those intermediate files. This is the API which enables to do that. And if you're interested in this API, I want to advertise the talk of my colleague, Brett Slotkin. It's called Large-Scale Data Analysis Using App Engine Pipeline API today. I think it's 4 o'clock something. So yeah, please come in if you're interested in running your own complex processes. And now I promised you a more complicated, more involving example of MapReduce. And the examples we're going to write is which I call distinguishing phrases. So the idea is to take a look at multiple books and figure out if some phrase is being used in one particular book a lot, but not used in the other books. Like if some authors have their own signature phrases, or some books have signature phrases. And the way we're going to do it is we're going to split the text into n-grams. N-grams is a sequence of n consequent words together. And you can pick the n which you like. So I ran the examples for n equals 4. The problem here, if you increase n a lot, like if you use 10 grams, then 10 grams are probably quite unique because these are complete sentences already, and they're quite unique. And if you use n equals 2, this is not even a phrase, this is just 2 words. So I picked 4. And for reduce, the first thing we're going to do is we're going to check if this phrase is actually frequent. We're not interested in something that author used only once. So we check if it occurred 10 times. Then we're going to check if a single author, or like a single book, has this phrase more than every other book combined, which means that this is really unique for these books because it's more than everyone else. And we're going to run this on the same data set, which is 90 books. Let me show you how it went. So it took like 7 minutes with something. This is, as I told, the UI which comes from pipeline library. So we have mapline, shuffle, reduce. If you actually open the shuffle, you can see that there are lots of like sort pipelines, and each sort pipeline is sorting one hash-based bucket. The way I explained to you. And yeah, so it finished in like 7 minutes, 25 seconds. Just to have an idea of how, if this 7 minutes is good or not, I wrote a simple Python program which uses the same MapReduce computational model, but completely in memory in a single computer. And on my, like in one thread, because it's Python. And on my computer, it took like almost 20 minutes to complete. So this is already faster than running a computer, and this actually scales. So if you increase the data set, you can just increase number of shards, and you're not supposed to see a huge time increase. And when I was creating this demo, I wasn't even sure that this is going to work. But it turns out there are lots and lots of unique phrases in books. And this is the output. There are lots and lots of phrases here which you could use. And here it is, money price of corn. Let's just check. Okay. No, this is not fair. This is just one book which always talks about money price of corn. Let's pick something else. This is Spanish. Yeah, is of the same. It's surprising that this is unique, right? Yeah, so you can see that there were 3 books which use the phrase only once, is of the same something, and there is 1 book which used it 7 times. Because I'm just curious, this is what is this? This is a notebook of Leonardo da Vinci. So you can say that in this book set, the is of the same phrase kind of uniquely identifies Leonardo da Vinci. If you have a huge corpus of text, I guess it might become really interesting. And this was all, like, if you throw in all the details, which I omitted here, like count occurrences, if you inline on functions, it's like 50 lines of code. It's not a big deal, and it's already something interesting. So this was all I wanted to talk to you about today. Let me summarize you something. So summarize what I was talking about. So starting today, I did a push like a couple hours ago into Subversion repository. You can grab the source code, and you can take a look at an example. Documentation is coming soon, and you can run small, medium, and who knows how big they can be with user space shuffler. We haven't actually pushed the limit yet. You can run those MapReduces today in Python. Java's going to come really soon. If you're interested in helping us to get Java implementation, just write us an email, and we'll tell you where we need help. And I know that there are already people helping us, right? Yeah. If you're interested in large MapReduces, like maybe we should call them huge MapReduces, get in touch with us. We'll give you the API to access the full-blown shuffler for certain terabytes of data. I don't know. So now I'm ready to answer any questions you might have.
Thanks. It looks like magic, but I didn't quite understand the shuffle part and the merge portion. As a framework, it looks very complete. But when you run it on Google App Engine, you have the task queues which allows you to do map. But as far as the merge and the shuffling is concerned, if you run it parallelly as different execution threads, you need to have a common place where you can do merge. It can either be a data store or it can be memory. If it's data store, the current Bigtable doesn't allow you to do a select for update thing, which means if you try to increment the same inventory from 2 different threads, right? So when you do an update and when you read something else, it gives you a dirty data, right?
So basically, yes, the pipeline API gives you some kind of synchronization points. It takes care of all of that by itself. It knows all the limitation of App Engine platforms. It knows that it stores data in data store. It knows that it's bad to access the same entity from multiple requests at the same time. And Pipeline API hides all that complexity for you. You just define a job as a simple Python function, and you say, okay, run it after this one completes and pass all the output to here, and it's going to take care of that for you.
Okay. Right. So where do we get? Because we are trying to do this for aggregate queries, and we are not able to figure out a way within the app engine.
It doesn't use any kind of aggregate queries. It uses key names in a really interesting fashion to achieve that.
Right. But key name, aggregating information is the objective of merging to a key name, right?
Yeah.
For a use case like aggregate queries.
Yeah, but just take a look at source code.
Okay, I'll probably look.
It's all open source. Anyone else want to be on tape? Great, so then we're done. Thank you a lot for coming. If you have any questions which you want to ask me off the record, feel free to come to me. Thanks a lot.